one other fun application is that you don't necessarily have to have just a single charge. You could have a force on lots of moving charges, such as in a current. So if we have a force on a single charge particle, QV cross B, let's think about a wire carrying a conventional current. So capital I is that way, and so we're talking about mobile electrons in the wire moving the other direction, so little I is that way. And we want to think about if we place this wire in the presence of a magnetic field, what's going to happen to the electrons? Well, let's say we have a magnetic field pointing out towards us. And again, it's important to keep in mind this isn't the magnetic field due to the current in the wire. This is the magnetic field due to something else. Okay, we just happen to have a uniform magnetic field here. So an individual electron moving in this direction would experience a force in what direction? Let's see, QV, or V cross B is up, but we have to multiply it by the charge, right? So we're going to get a force pointing downward. So electrons would actually be deflected downward. And since there's so many electrons, we would actually see a force on the wire. It's a little bit subtle. We'll get to this when we get back to break. But what happens is you'll get a polarization here, and that polarization can actually create an electric field which exerts a force. Okay, so it's sort of an electric effect, but we can at least calculate the magnetic force. Okay, so we'll clear that up after the break. But essentially, we're getting a magnetic force on moving electrons. So we could calculate this as thinking about just a whole bunch of electrons in a segment of a wire. And doing the typical sort of thing, I'm going to break this wire up into pieces. And so here's one piece, and I'll call the length of this piece delta L. So to get the total force on all the electrons in the segment of the wire, I would need to find the number of electrons in the wire, right? I could just say that the total force, I'll call it delta F, to indicate that this is the force on just this piece delta L. Okay, there would be another force, there would be a force on this piece and a force on this piece and so on. If I wanted to find the total force, I'd have to add them all up. But the force on just this piece is going to be the number of electrons times the charge times their velocity cross B. Okay, so capital N is just the total number of electrons in this segment. And as usual, we can relate this to the electron density, right? We can say that the number of electrons is equal to the number of electrons per unit volume times the volume. What's this again? Number of electrons per unit volume. We called that, what symbol did we use for that? Not U, that was N, right? Little n, little n. Okay. And the volume of this segment would depend on its length and what else? Cross-sectional area, cross-sectional area. So we need to know that, right? So it's going to be cross-sectional area times this delta L. Let me plug that in. We're going to have, I'll bring the Q out front. Q times N times A times delta L times V cross B. Well, let me do a little bit of rearranging here. I'm going to have Q, N, A. Let me just think about positive charge motion. So if negative charges are moving that way, I could also say it's positive charges moving that way. And I'll call delta L, the vector delta L, the direction of the conventional current. So that vector is delta L. It's pointing in the direction of capital I. So I'm basically putting the direction on top of the delta L rather than on top of the V, just to isolate the V here. Well, what is the charge times N times A times the drift speed? That's what? That's the current. That's the conventional current, right? That's the conventional current. So we could also write this expression or this relationship between magnetic forces and moving charges in terms of the current and say that delta F is equal to delta I delta L cross B. Okay. By the way, can't remember if I remember that said this last time, but this is a formula you should just memorize. And so that'll be the last, I believe, the last major principle you'll have to just commit to memory. This one would be on a formula sheet on a test, so you won't have to worry about that so much. But the other one is, again, sort of the fundamental idea, how charges are affected by fields. So you should just know it. But if you have a conventional current in a wire, this says that we should be able to find a magnetic force on the wire based on the direction of the conventional current and the magnetic field. So if delta L points in the direction of conventional current, let's just test it. I is pointing that way, right? So I delta L cross B, thumb points down, which is what we said before for the magnetic force on the electrons, okay? Well, now is that going to be a noticeable effect? Let's see if we can come up with an estimate for it. Let's say I have a wire, or at least a segment of a wire. It's a thin copper wire, so we're going to look at kind of a little wire like this. Maybe the length is, I don't know, maybe 3 centimeters long, okay? And the current, let's say we have a fairly strong current running in it, I don't know, maybe a couple of amps. We're basically going to apply a potential difference across here with very little resistance, so we can get a fairly high current. I'm not sure if there is a rating on here. Well, when we turn it on, we'll see. It'll say a few amps, okay? So I may be, I don't know, 3 amps. Delta L, maybe 3 centimeters, so 0.03 meters. Magnetic field. We're going to put it in a magnetic field that's due to a fairly strong bar magnet. Strong bar magnet can make a magnetic field on the order of Tesla, half a Tesla, something like that. Let's just call it 1 Tesla. So we end up with a force that's equal to, or a force on this segment. Let's say the magnetic field again is pointing in some direction. And a current's going that way. So the force would be, the magnitude of the force would be the magnitude of the current times the magnitude of delta L times the magnitude of B times the sine of the angle between the current and the magnetic field, which in this case is what? The angle is what? 90 degrees, sine of 90 is 1. Okay, so I times delta L times B. We have 3 amps times 0.03 times 1 Tesla gives us 0.09 newtons. Is that going to be a force big enough to notice? It's going to depend on the mass, right? How big? Thin little wire. Approximate mass of what? Kilograms? Grams? Yeah. Few grams? 10 grams? 20 grams? Maybe. Let's try 10 grams, okay? We want to figure out how much it's going to accelerate. Let's say, just using F equals ma, the acceleration is going to be about then 0.09 newtons over a mass of about 10 grams maybe. 10 grams is 0.01 kilograms. That's an acceleration of about 9 meters per second squared, right? If I work the units out. Well, that's on the order of what? That's on the order of acceleration due to gravity. We might be able to see something. Let's try it out. We've got a power supply here hooked up to, here's the positive terminal. Positive terminal, let's see, I got the wires kind of crossed here. Positive terminal going into this end, and then I got a little trapeze here. I have a hanging wire. Let's see if I can arrange this a little bit more carefully. I have a hanging little trapeze where the conventional current is going to flow down this way, across this segment, through a magnetic field here, through a bar magnet, top and bottom. That's got a magnetic field, and this pointing, I think it's going to be pointing downward. We can check that. Back up, okay? So I have a current running that way, conventional current running that way, magnetic field pointing down. What should I see? A force in what direction? I cross B, out towards us, right? Let's try it. Lo and behold, wire actually bounces out in front. Can everybody see that? If I arrange this, maybe sideways view might be a little more easier to see. Turn the current on, and you can quite clearly see the wire bounce out in front, and then it's getting stuck here. Let's see. Okay. And if I were to reverse the direction of the current just by flipping the leads here, we should see a deflection in the opposite direction, right? So let's try that, and it does do that. Okay. So if you get high enough currents, this is not something you might see with just sort of a refrigerator magnet in one of the circuits you built in the lab, right? But if you have a high enough current and a high enough magnetic field, because there are just so many electrons in here, the force is actually pretty sizable, okay? And you can actually measure it. Okay? So jumping wire, kind of a fun little demo. Okay, maybe let's try one quick question on this, just to make sure we're okay. And, well, we've basically done this, but let's do it again. I got to start this up. Come on, there we go. So conventional current, capital I, pointing to the right, magnetic field into the screen. What's the direction of the magnetic force on the wire? Okay, so let's see. We have magnetic. Let's just reminder of what these symbols mean. A little circle with an X through it means what? Vectors pointing in, right? Okay, so that means B is in, capital I is to the right. So that means the delta L vector is to the right. We take our fingers, point them in the direction of capital I, curl them toward B, I delta L cross B, thumb points up, and that's on this choice of axis, that's going to be the positive Y direction. Okay, so 3 is correct. 3 is correct. Just be careful of signs again. That if we're talking about delta I, we mean the motion of positive charges. Even though we may really have electrons moving in the other direction, you can't tell the difference, right? If we had electrons moving that way, because of the sign flip, you'd still get a force upward. If we have positive charges moving that way, you get a force upward. Okay, so based on this effect alone, we can't tell the difference between negatives moving one way or positives moving another. We're going to start talking about some things today that will lead into an effect where we can tell the difference between positives moving in one direction or negatives moving in the other direction. So we'll deal with that when we get back from break. We'll start building up to that today. Everybody okay here? Questions on this? Yeah, question. Yeah, so if you want to do that, that's fine. But you have to then remember they're electrons, right? So if you have little I, electron current moving in that direction, you can say V cross B is down, but then you have to multiply by the negative charge of the electron, which would give you a force upward, right? Okay. Other questions here? Everybody okay?